Welcome back, ladies and gentlemen. In this video, we're going to be checking out this idea of conservation of momentum, and this is section 9-4 in your textbook. Now, when something is conserved, so this idea that we've heard before, conservation. What this really is telling us is that its value is constant. So this is kind of just equating something to being constant. Fair enough. But with momentum, when is this true? When is momentum conserved? So let's look at this idea of when is the change in momentum equal to 0? Well, that's going to mean that its value is constant, right? If there's no change. So we're going to see that final minus initial momentum is 0, or that final momentum is going to be equal to initial momentum. It's all the same thing, all the same. We're asking the same question here. When is the final equal to the initial? When is the change going to be 0, right? So recall that sum of forces is going to be equal to the change in momentum divided by the time interval. Or another way of saying it is, well, sum of forces is equal to the rate of change of momentum. Rearranging this, we look at the change in momentum and we say, well, all right, it's equal to sum of forces multiplied by the time interval. And here's the deal. We want this to be 0. Well, what's going to be 0 on this side? Can we say that there's some forces acting on something for 0 time? That doesn't make any sense. So instead, we'd say that when there are no forces acting on an object, when the sum of forces is equal to 0, then the change in momentum will be 0. So in other words, if there's no net force acting on an object, the object will experience no change in its momentum, and therefore the final will equal the initial over any time interval, right? So in order to make this work for us, we have to sort of separate forces into a couple different categories. And it's pretty straightforward, pretty easy to see this. But we're going to be checking out external forces and internal forces. External and internal forces. All right. So this idea of the sum of the forces acting on an object. Well, of course, it comes from the sum of the external forces plus the sum of the internal forces, right? It just has to. By definition, this is everything, and therefore we have to add the external plus the internal. Now, the idea of an internal force. So internal forces basically are forces acting on the system and originating within the system, right? It's kind of like something pushing on itself from within, so to speak. These guys always end up canceling out. Always, always, always. 100% of the time. Internal forces cancel out when you look at a system. So because of that, internal forces do not contribute to a net force. They basically go to 0. So they do not contribute to the net force acting on an object. Imagine this. Get inside a car. You're sitting behind the steering wheel. You close the door and you push on the steering wheel. You cannot expect the car to start to accelerate forward. You can push as hard as you want, but the car will not go anywhere because of the force you're exerting. The force you are exerting is an internal force. Yes, it exists, but it ends up canceling out. It does not contribute to the net force acting on the car. And essentially, this is Newton's third law at play because, well, for you to push forward on the steering wheel, you have to push backward on the seat of the car behind you, and you end up canceling things out. Therefore, the steering wheel is pushing you backward, and the seat is pushing you forward, and it all sums to zero, right? So, some of the internal, not some of, but the sum of the internal forces will always be zero, and therefore we can say that the sum of forces acting on an object is simply only equal to the sum of the external forces that are acting on the object. Because of this, we can have another therefore. The change in the net momentum of a system, well, that's going to be equal to only the sum of the external forces multiplied by the time interval over which those forces act, right? It used to be that we would say simply, well, it's just the sum of forces multiplied by the time interval. Well, now we see that any internal forces, like you sitting in the driver's seat pushing on the steering wheel, that's an internal force. Any internal forces do not contribute to the net force that are acting on the object, because internal forces always cancel out. And so we're rewriting this relationship between the change in momentum and force and time to only specify those external forces. Now, the deal with external forces, they may or may not, I think this pen needs to be retired here. All right. Let's set that one out to pasture. Well, that's, oops, not net. I wanted to say external. There. External forces. They may or they may not might or not sum to zero. It depends. It depends on the situation. It depends if there is a leftover unbalanced force, or if there is no leftover unbalanced force acting on something. And we would take it one way or the other. We would say, well, if there's no leftover unbalanced force, then there would be no change in momentum of the whole system. But if there is an unbalanced force, then there would be some change of the momentum of the system. Okay, so now we've got this idea of internal and external forces dealt with. So internal forces have no effect on a system. That's internal forces have no effect on a system. If the external forces acting on a system are, if the net external forces, or if the sum of the external forces acting on a system is zero, then the system's net momentum is conserved. Then the system's net momentum is conserved. Okay, that's a pretty important statement right there. Now, okay, I don't know, the word system might still be throwing a few people off. A system is whatever you want to define it as. It's any single object or any group of objects. It's really arbitrary, completely up to you. But once you define what the system is, then instantly should be clear what are the external forces acting on it and what are the internal forces acting on it, and you work from there. And you have to stay consistent. So if you define the system to be two things, well then the system will be those two things for all the calculations you perform. If you change the system, if you incorporate a third thing, if you eliminate one of those two things, you have to redo those calculations and see what the new relationships might be. Well, what this is saying, though, we can look at this and say, well, the momentum of object 1 in a final sort of state, so after something happens, plus the final momentum of object 2 plus that is going to be equal to the initial momentum of object 1 plus the initial momentum of object 2 plus however many objects there are. So we see that the sum of individual momenta before and after is the same. There is no change in the momentum of the whole system. Another way to look at this is net momentum, and this is equal to the sum of all individual momenta, right? However many parts there are. Well, the value of this is going to be constant. No change. Well, okay. We could also write it like that. Change in net momentum of the whole system is 0. No change, right? This is sort of three ways of expressing the same idea. The idea that's expressed here in the sentence. You could say, well, I'm going to add up everything that's after an event, and it should equal everything before the event. I'm going to look at the total momentum of the system by adding up all the parts, and that total would be a constant value before and after the event. I could instead talk about the amount of change in momentum of our system, and there will be no change in that momentum of our system. So here's the deal, though. Keep in mind that this does not mean individual momenta are constant. It does not mean that. You might say to yourself, well, look, you just said it, Woods. You just said that the final momentum of object 1 is equal to the final momentum or initial momentum of object 1, and therefore from these two things coming right there, you might say that, well, the change in momentum of object 1 is 0. And the problem is that's not true. That is not what I said. That's not what's going on here. Look, if I have these two objects, object 1 and object 2, and I say, you know what, before an event happens, object 1 has momentum 10, and object 2 has momentum 2, right? What's the sum? Well, the 10 plus 2 is going to get you 12. All this is saying is that the net change is 0. So if you have 12 before, you have to have 12 after. But it does not tell you where the 12 have to be. It does not tell you how it must be distributed. So where object 1 may have had 10 to begin with, and object 2 had 2 to begin with, object 1 might have 2, and object 2 might end up with 10. But it doesn't have to be an even swap. They might both end up with 6. Or one of them might end up with 0 and the other one with all 12. This is not dictating at all what's happening to individual parts of our system. This is only dictating what's happening to the whole system itself. That's it. So when we get to examples and dealing with collisions, this is going to be really, really critical. And you'll see it. It's going to be very clearly illustrated for us, right? But the only thing here that's really being said is this is about as simple as it can be made right here. The net momentum of the system, the overall momentum of the entire bit of parts that we're considering, does not change. The change is 0. That's all we're saying. Now, let's get to an example. So in this example, let's look at, in fact, I'm going to steal this one from the book because it's a great one. This is going to be example 9-3 from your textbook. And they talk about two canoes on a lake. And I will try my best to draw for you two canoes on a lake. We're going to say, give yourself some room here. Canoe, water line, and canoe, water line. In fact, this is just one water line, right? Okay, two canoes on a lake sitting nearby each other. And here's our situation. We have canoe 1 and canoe 2. Here's 1 and here's 2. And we know their masses, and they have different numbers of people inside. So let's go. Mass of 1 is 130 kilograms. And mass of canoe 2, 250 kilograms. So canoe 2 is carrying some more people than canoe 1 is. Maybe there's a person there and a person there just enjoying the day. And in canoe 2, we've got a whole party going on, right? Getting a little crowded in canoe 2. But you get the idea. More mass. So let's say they met, they had a powwow right in the middle of the lake, saying hi to each other, good friends, good times. But they're done. They want to go on their separate ways. And so this person is going to push right here on canoe 2. And that's this person pushing on canoe 2, applying a force. So we are going to say that, you know what, there's a force here. And this force is a force acting on 2. And it is a force, a value of 46 newtons. Okay, fine. Well, look, okay. Action, reaction. Newton's third law. You cannot escape it. So because of this push, there's also this force acting on canoe 1 of 46 newtons, right? It is unavoidable. But there's an important distinction here, and that is we are dealing with vectors. Direction matters. So we're going to say, you know what, we're going to make to the right the positive direction. Awesome. Well, that technically is going to mean this 46 newtons acting on canoe number 1 is in the negative direction. So I could put a minus sign in front of that. And I will have to in just a moment when I deal with these things, right? So we're going to need to find the momentum of each canoe. And we're also going to want the velocity of each canoe after that push. Now, if we're going to do that, we'll need to know that this push occurred for a certain amount of time. There was a time interval of contact, and the idea of the contact of this person, pushing on this canoe to separate them, to get them moving away from each other. That interaction took a period of time. Let's give this a period of time of 1.2 seconds, 1.20 seconds. And once contact was broken, they are no longer interacting with each other, and the force goes away, and they're kind of doing their own thing at that point. So, after 1.2 seconds of pushing, we need to find the velocity of each canoe. To get the final velocity, we'll need to know the acceleration of each canoe, and so we'll have to use Newton's second law. Acceleration is ratio of force to mass, or force divided by mass, essentially, right? And also we're going to have to use, well, we have a final velocity equals initial velocity plus acceleration times time. And why bother going about all this? Well, remember, momentum is a mass times a velocity. And if we're going to want a momentum of canoe 1 and a momentum of canoe 2 after this push, Well, then we need a velocity of each canoe after the push. To get a velocity after the push, we need to know the rate of acceleration and the time interval. And we got the time interval, and the rate of acceleration comes from force divided by mass. So we have the information we need. We just have to recall the relationships that we have to use here. So let's get this going. Canoe 1. So the rate of acceleration of canoe 1. This is going to be pretty easy. We have a force of 46 newtons, but you must remember, please, that this force is in the negative direction, right? Negative 46 newtons divided by the mass of canoe 1. That was 130 kilograms. And so canoe 1 is accelerating at a rate of negative 0.354 meters per second squared. That's an M. Awesome. Well, from now this relationship, I want that final velocity of canoe 1. And the initial velocity is 0. They were simply sitting there as they talked with each other. And so I simply need acceleration times time. So I have negative 0.354 is my acceleration, and my time is 1.2 seconds. So I get a value for this final velocity of negative 0.425. meters per second. So that's how fast canoe 1 is traveling after the push is done. Awesome. Well, then if we know the velocity after the push and we know the mass of the canoe, we can find the momentum of canoe 1 after the push. It's just mass times velocity. So I have a mass of 130 kilograms. And this velocity, negative 0.425 meters per second. The momentum of canoe 1, I get negative 55.3 kilogram meters per second. So I have found the momentum. That's just off the bottom of the paper. Sorry about that. Trying to squeeze it in. I found the momentum of canoe 1 after the push. Brilliant. So I must do the same thing now for canoe 2. So canoe 2, it's going to experience an acceleration due to that force, and I'll divide by the mass. So the force, now for canoe 2, it's 46 newtons acting on canoe 2, but that is a positive force. It's in the positive direction, right? So I have 46 newtons, and the mass of canoe 2 was 250 kilograms. And so the rate of acceleration I get for canoe 2 is in the positive direction, but 0.184 meters per second squared. Now I want a final velocity. For canoe 2, I need my rate of acceleration times the time interval. Time interval is 1.20 seconds. The final velocity that I get, 0.221 meters per second. And so now I can figure out the momentum of canoe 2 after this push. I simply use, again, mass times velocity, and so the mass is 250 kilograms, and the velocity is 0.221 meters per second. So the momentum of canoe 2, I get 55.3 kilogram meters per second. Wait a second. Wait a second. You're telling me that after this push, canoe 1 has a momentum of negative 55.3 kilogram meters per second. Canoe 2 has a momentum of positive 55.3 kilogram meters per second. And the answer is, well, yes, of course. So let's think about what's going on here. What was the total momentum of the whole system? Sorry, get that lined up for you. The total momentum of the whole system before the push. Total momentum. The whole system would consist of both canoes combined. And so if we look at that situation, well, before the push, they're sitting there. They are motionless. Neither one has any velocity. So neither one has any momentum. So the total momentum would be 0, right? Another way to look at that is the sum of the momentum is 0. I could also write that as net momentum is 0. Awesome. Well, what about, that was before, right? How about after the push? Well, what's the deal after the push? Oh, well, I simply say, well, the sum of the individual momenta. Get my symbol done. That's going to be the momentum of 1 plus momentum of 2. And that's going to be negative 55.3 plus 55.3. And that's going to be 0. How about that? So I could also say the net momentum after equals 0. Right? So what does this tell us? Our total momentum before the push is 0. Our total momentum after the push is 0. What we've seen is that momentum is conserved. The change in momentum is 0. So how can this be? Well, how about that push? Wouldn't the push have affected the momentum of our system? Well, no. This push, turns out, is an internal force. Recall an internal force. It acts on the system, but it originates within the system. This push originated with this person in canoe 1. It came from canoe 1, essentially, which was already part of the system. It was not external to our system. So the system as a whole, the whole thing here, had no change in momentum. It was constant because that's only an internal force. There were no net external forces acting on the system. So we saw an example here of conservation of momentum, right? Awesome. Well, here's what we got from that. We got the change in momentum was 0. We could also say from that the sum of the forces that are external to the system is 0, right? Because it was only the one internal force that accelerated each canoe separately. Check this out. If we were to define a different system, if we were to say, you know what, we're only going to look at canoe 2 as our system, then check this out. This push is now coming from a source outside of our system, isn't it? That push would become an external force. And if that were the case, then the sum of external forces would not be 0. We would not see momentum conserved. The momentum of our system would change because of that external force. But we didn't. We had this whole system that we were considering, and it did not change. That's pretty cool stuff.